Let's talk about impulse. I want you to consider this ball being hit by a baseball bat, and in order for it to go flying, it has to experience a net force acting on it from the baseball bat for a certain duration of time. And that's exactly what impulse is. The symbol for impulse is lazy J, a capital J, and it is the product of the net force acting on an object and the contact time through which that force acts. The unit of impulse is Newton seconds because the unit for force is newtons, and we multiply change in a duration of time, which the SI unit for is seconds, and so we get the unit to be simply just Newton seconds. Please don't say newtons per second, it is just the product of force and time, so Newton seconds. So the formal definition for impulse is defined as follows. It is the product of the net force acting on an object and the contact time that the net force acts. So the formula for impulse is F net delta T, as we've seen, and we actually write the symbol for impulse as capital J, written cursive. So we have seen just previously that we can express Newton's second law in terms of momentum. So from first principles of Newton's second law, we know F net is ma, which eventually gives us that F net is delta P over delta T. This is Newton's second law in terms of momentum, which we have already defined. And now if we multiply away with delta T to the other side, what do we get? Simply an algebraic rearrangement, we get F net delta T is equal to delta P. That formula is known as the impulse momentum theorem formula, and it states the following in words. The impulse momentum theorem states, we have already defined Newton's second law in terms of momentum. So the impulse momentum theorem, which has the formula F net times delta T equals delta P, states that the change in momentum, the right-hand side of that equation, the change in momentum of an object equals the impulse applied to it. So as you know, F net times delta T is what we have just defined as impulse, and so we can say that cursive J is equal to delta P. So the change in momentum of an object equals the impulse applied to it. That is known as the impulse momentum theorem. So just again, it states the change in momentum of an object equals the impulse applied to that object. And here's just a little illustration of what that means. In order to stop a moving object with momentum, a force has to be applied for a certain duration of time. And this is basically what that states as a formula. It states that F net delta T is equal to delta P. Yet again, in order to change the momentum of this rugby player here with the white shirt, the rugby player number 15 in the Navy has to apply a certain net force for a certain duration of time to stop that player in white. So in order to change its momentum from some high velocity to zero to stop it, or to some other velocity if it's going to rebound in the opposite direction, a certain net force has to be applied on this rugby player for a certain amount of time. Now, it's really important to take note that you can change the momentum or the mass in motion of the rugby player coming towards you in one of two ways. You can either apply a huge amount of force for a small period of time to change his momentum from some high value to zero. To get that same change of momentum by applying a force, if you are not that strong, you can be quite clever about it and simply do the following, right? You can say, all right, I can only apply a small amount of force. So how will I still bring this rugby player to a halt? I have a small net force that I can exert on this rugby player. In order to bring it to a halt, I just have to apply that net force for a longer period of time to eventually tackle him to the ground and change his momentum from a high value to zero. Right, so it's a very important concept, this change in momentum due to a force being applied for a certain interval of time. That concept of the momentum impulse or impulse momentum theorem. For this car with a great amount of mass, it has to change its momentum from high value to zero, and therefore it's going to apply brakes. The brakes will be the net force acting, that is in fact friction, and it's a negative value. It's going to act for a certain interval of time, and eventually the car can change its momentum from a high value due to a high speed and a combination of speed and mass to zero. If we look at another type of impulse being changed due to force acting over a period of time, this guy here has a much smaller mass, right? So yet again, its momentum has to change, right? But a certain net force from the snow, which again will be friction from the snow acting for a certain period of time or interval of time, have to act on this person to bring him to a halt and change his momentum from a high value down to zero, to stop.